Welcome to Data Science 1, probability density functions. All right, so things we need to remember. We need to know what a sample space is, what a random variable is, a continuous random variable, which we talked about in the last video, and the cumulative distribution function. So back to our fishing example that we talked about before. So the random variable here is continuous in the sense that there's too many options to count on the values that it assigns along the real line. So we decided that we would use the cumulative distribution function, which is, well, it could be approximated by the number of fish smaller than x over the total number of fish. So I can get a distribution for this that I don't need to look at each one individually and count the number of the ones that were exactly the same, because it's very unlikely that they'll actually be exactly the same. And we didn't like it because it was really hard to interpret them. If we look at it, see, here are three of them, three CDFs, and you can see there's a shift, but it's really hard to see what's going on. So what we'd like to do is to maybe take a different approach at looking at this. And you have to remember, these are CDFs, so they're not like the probability distributions we looked at for discrete. They're a little bit different than that, and that's where we have to really focus in and get something usable. We want something like the other one. So if I use some calculus and take my CDF and differentiate it, I get pictures like along the bottom, and the ones along the bottom look far more similar to the ones that we saw for the probability distributions for the discrete. Okay, the problem here is that these aren't probabilities. Okay, the height of that thing is not a probability. So you can see the shape easier, you can see the center easier, but what does it mean? Okay, so what are probability? They're called density functions. They reflect how quick the probability is changing across the CDF. And you're like, okay, whatever that means. But you can think of them as they represent how likely the value of x is. Not the probability, but how likely. So I can use it to compare it to other values of x and see which one is more likely to occur. But before we really get into that and start playing with lots of distributions, which that's the only way to get comfortable with this idea, is we'll see lots of distributions as we go along here, but we need to pay attention to the relationship of the CDF to the actual the probability density function. So how are they related? Well, you can use the fundamental theorem of calculus, and if you're not familiar with the fundamental theorem of calculus, well, here it is. So the probability that a value, our random variable, is less than x is what our cumulative distribution function is. And it can be represented as the integral of f of t dt from negative infinity to x. And you're like, well, that's really useful. You didn't tell me what f of t is. Well, if we look below, we can see f of x is simply the derivative of the cumulative distribution function. However, f is so much easier to think about when it relates to probability. Okay, so for example, we can just say, well, what's the probability that x, our random variable, is between two numbers, a and b? Well, that's simply the probability that x is less than b minus the probability that x is less than a. Okay, this is, well understood because probability behaves in a certain way, which is f of b minus f of a, which is, if I apply this definition here, negative infinity to b minus the integral from negative infinity to a of f of x dx, which is the integral from a to b of f of x dx. And you're like, so what? Okay. This doesn't really help me because this is the first time you've seen it. And if it's not the first time you've seen it, then you probably know the punchline here. So look at what we're doing. We're finding the area under the curve between A and B. And if you remember way back when we started, what did I say? I said probability behaves like area. We're finding areas under the curve. And since probability behaves like area, this is a very natural way to think about things. So as we're going along here, don't be intimidated by this calculus because, like I said, I'm going to show it to you. I'm not going to hide it from you. But at the most of the time, we'll be able to work our way around it because somebody will have done the heavy lifting for us. All right, so since it behaves like area, if this is our probability density, and we wanted to know what's the probability we're between 2 and 4, our random variable falls between 2 and 4, we just integrate this thing from this region here, and we can come up with its probability just by doing the mathematics. Now here I don't have the density listed where we work everything out. We're going to leave that to the individual distributions as we go along. So we're going to look at a variety of distributions as we go along, and you'll see how this all fits together. All right, so quick summary of what we've been talking about here. So CDFs are useful to help us define probability, but they're really hard to interpret directly. PDFs allow us to look at the distribution similar to what we did before, and that's what makes them so useful. We can find the probabilities by simply integrating, and if you think about it, what did we do to find the probabilities of intervals when we were doing things in the discrete space? Is we were summing, okay? PDFs have some properties that we should mention. They're always positive, and they're going to integrate to 1 if we integrate across the entire real line. These properties are similar to those of the discrete distributions, except the sum is replaced with an integral, and that's the only difference. You can think of this integral sign here as just a sum, because it actually is. Another interesting property is that, what if I wanted to know the probability that x equals exactly a little x? Well, if I apply the definition here, okay, then I get from x to x, which is 0. This isn't the official proof, but it gives you some idea here. The probability of any individual outcome is 0. Okay, so you can't talk about the probability of an outcome like you did before. And I want to make sure that that's clear here, because as we go along, when you're in the discrete space, you just plug in the number and you get out a probability. Here we can't get a probability of a specific number because it's in a continuous space. So just keep that in mind as we go along and move on to the next video, which is about expectations again, which we seem to have just covered for the discrete case. See you there.